Also, Brian is here.
Brian is here. Okay, cool. I'll make him co-host
Mhm.
while I introduce myself. Okay. Yeah, my name is Justin. I've been doing math competitions for a while. Maybe you've seen me. Make co-host.
Justin, don't be humble.
I've been doing competitions for a while. This is a fun. This is a fun topic. I'm excited because we are going to be talking about the functional equation at some points in here. So it's gonna be fun. Brian, you have everything set up? Everything's good for you?
Yeah.
Okay, cool. All right, then we're gonna start with some review. I'm hoping that most of you went to Monday's class where we talked about basic polynomial stuff, but here's just a bit of some tricks.
Oh yeah, and by the way, if y'all have any questions about anything, just message me or Brian.
Yeah.
We'll
All right.
respond to them.
If I ask questions, please send them to me so I can just see like what you all are thinking. But all right, I'm just gonna review some subjects really quickly. All right, so first off is just some of like the harder stuff in the end. All right, so first off, let's go with the Vieta's formulas. And we will actually get to this in a later section, covered in a bit more advanced way. But let me pull up chat also. And then drag it to a place where I can see it. All right, the Vieta's formulas. So I want you to consider this quadratic that I'm writing down right now. X squared minus bx plus c equals 0. All right, can people tell me what the sum, okay, let's say this looks like x minus r times x minus s. Can anybody tell me what r plus s is equal to? Right, I'm getting a lot of b's, that's correct. Notice that I have a negative b right here, and if we were to expand this out, these would actually be negative signs. So it is positive b, the sum of r plus s. Can anyone tell me what r times s is equal to? And I get a lot of C's, and yep, that's exactly correct. Because that should just be an RS. Okay, cool. So generally when you're working with polynomials, you always want to make them monic, which means they look like this. This leading coefficient is 1. And that makes a lot of expressions cleaner. It might make these rational numbers, which maybe fractions you don't want to deal with, but most of the time it's worth it, especially when we have general cases like this. All right, so I'm going to do this except x cubed plus ax squared plus bx plus c. All right, this time the roots are r, s, and t. All right, can anybody tell me what r plus s plus t is equal to? I'm getting a lot of negative a's. That's correct. Remember, we want this to be negative. All right, can people tell me what r st is equal to? Okay, I'm seeing a good mix of, I see a few B's, most of the people are saying C, but I see a lot of positive C's and I see a lot of negative C's. It turns out it's negative in this case. The reason is because this is 1 jump and this is 3 jumps. With our x squared plus bx plus c, the c term is only 2 jumps away. So the 2 jumps means a positive, the 3 jumps means a negative. Think about it. Think about the sign of this. Negative r times negative s times negative t is equal to negative rst. So we have to negate the c. All right, this could be a common mistake if you're just blindly relying on the formulas, which is why I should strongly encourage you to always think about the factored form and what it looks like when we expand it. So on that note, what is equal to b? All right, I see b is equal to b. Yes, that is absolutely correct. All right, and I'm saying this, rs plus rt plus st. And that's exactly what it is, because like you multiply these two and then you multiply by x, or you just do the same thing the other way around. You just expand it with FOIL and you will get this, I guarantee it. I see a couple people mentioning that this is like a symmetric sum. We will get into that later. Another thing to note, This is positive. So we see the sort of general trend here when we have these expressions. We have a negative here, positive here, negative here. All right, remember, we always start with a negative. Right, and you can hopefully see that this pattern continues for future, but usually you don't need to go that high. The second thing that I want to review is the Sophie-Germain identity. And it is the closest we can get to factorizing the sum of the squares. All right, does anybody remember what this factorization is like? All right, I see a couple people remember it. I also see what is known as the freshman's dream in the chats, which is the assumption that this is true. Well, as much as I would love for this to be true, it doesn't work because there's a lot of terms in between that mix these. Yeah, if you look it up on Wikipedia, look up freshman's dream. It's actually a thing. All right, I'm seeing the factorization. I saw one person who, which I love, told me how we get to the factorization, and that is difference of squares. All right, I'm going to write it like this. All right, does everybody see how we get this first one? All right, we go like this. Something that isn't, I think, really mentioned in like the Polynomials 1 or this class for that matter is recognizing that you can factor like this. Figuring out perfect squares, perfect cubes, even perfect fourth powers sometimes can be really useful. And then how does this look? 2ab squared. So hopefully you all remember difference of squares. This is like our x and this is our y. So we have x plus y and x minus y. Like so. All right, so this is the Sophie-Germain identity. All right, if you see something that like, you know you're supposed to factor, but you don't know like how to do it because it's like a sum of squares or something, think Sophie-Germain. It might get you out of a nasty spot. All right, hopefully you all remember the standard factorizations. We will go over some more in here. And finally, I want to go over something that's not mentioned in either of these handouts, but can be a useful trick, and that is the remainder theorem. Basically, this goes with polynomial division, which honestly we should have included in the handout. Maybe I'll make some bonus content. I don't unfortunately have it really right now. But let's say you have this polynomial like that looks like x squared plus x cubed plus 6x squared plus 5x plus 3. And you want to divide it by x minus 3. All right, this is the equivalent of writing this polynomial as like x minus 3 times some quadratic, which I think looks like this, plus a remainder. All right, and some of you are saying synthetic division, that's what this method is. I won't go into it here, but the important part is there a fast way to find out what this remainder is? The answer is yes. It turns out all you have to do is plug in 3. And the reason is because this term, this entire thing goes away because you have a 3 minus 3, you multiply by 0. So this becomes 27. All right, this becomes 2 times 27. This becomes 15. This becomes 3. And when you add that all up, I believe you get 99. All right, and the important thing is what happens when this remainder is 0. That means that you found a factor, and that means that you can just pull it out. This is known as like the remainder or the factor theorem. I believe the factor theorem is a subset of this. If I'm being honest, I've only seen this question like ever once, and it was like something that would use this once, and it's this year, but knowing it and being familiar with it is good just for general like polynomial intuition. All right, hope if you have any other questions, please direct them to Andrew or Brian. And now I will go to what I have prepared for you. So we're just gonna go straight into problems. And give me a sec. It takes a bit of effort to like be able to switch between 2 different screen shares. It's kind of annoying. Oops. That's spoiling. All right. I should have added Brian Liu here because he is also here. All right, let's just get into it. All right, here just some like miscellaneous factorizations that maybe some of you already have memorized. That'd be great, but these are just like good things to know, good tools to have in your arsenal, just things to try. Just knowing that it is possible, and hopefully they will demonstrate the techniques that we need. All right, the first 3 are more common. The last one, not so much. Right, so please copy these down. Please copy this down. I'll actually post all of them in the chat right now. Y to the n, just a list of all the ones we're gonna do. And just think about how we might factor these. All right, see if you can draw any connections to any factorizations that you already know. And then after that, all right, I think that's everything. And all right, can everybody see the whiteboard, hopefully? Cool. So let's get started with the first one, x to the n minus y to the n. So this is like a generalization of things like x squared minus y squared that we've seen before, and x cubed minus y cubed, which I believe both of these were gone over on Monday. And these are what they look like. Now, hopefully you can see, what do these have in common? We have an x minus y factor in here. So is there a factor that like we expect this to have in general? Yeah, we expect this to have an x minus y as well. But the question is, what is the rest of it gonna look like? Like, what is this mess gonna look like? All right, okay, so we see that we have like an x term here, we have an x squared term here. It makes sense that we have like an x to the n minus 1 term here, because how else are we gonna get this x to the n through multiplication? Like here. But what we have right now is we have like x to the n minus y x to the n, or okay, notice that I'm taking extra precautions to make sure that my variables stay in alphabetical order. And this is good because it allows me to be more organized and make less mistakes. But now we have this, and we don't want this. We want to get rid of this. All right, that was caused by this multiplication. So maybe we need to multiply x by something to cancel it out. All right, is there anything? All right, we want to add that. We want the rest of these to contain a term that like when multiplied by x will equal positive x to the n minus 1y. And I see somebody says x to the n minus 2 times y, and that's exactly what we want. Because now when we multiply these two, this is exactly what we get. Perfect. But notice again, we have to also multiply it by y. So we have another problem. We need another term to cancel this out. Notice that it's a y squared this time because you have y times y. So what other term could I add here that would cancel out this x to the n minus 2y squared? And what I would add is x to the n minus 3 times y squared. Because when I multiply this by x, the only other term that I can multiply y with, I get plus x to the n minus 2. And I think you see where I'm going with this. We're going to end up adding this. And we keep on going. And can anybody guess what the last term is? Y to the n minus 1. So what this looks like if I plugged in n equals 5, for example, and this might make it easier to appreciate the structure. X to the 4th. So you can see that the powers are like slowly being transferred over. 4, 0, 3, 1, 2, 2, 1, 3, 0, 4. So yes, it turns out this factorization will always work. And hopefully there aren't any more questions about this. So let's go to the next one. And I might have to go a bit faster because it looks like I used up more time than I expected in the beginning. So I'm gonna go with, and I'm just gonna glaze over this really quickly. All right, because this is more or less the exact same. Because let's say we have this, and we replace this y with a negative y. All right, it's still like, it would still be the same factorization, except now we have this term. We're adding like 2n plus 1 powers instead of subtracting them. All right, this 2n plus 1 that I have here is only to make sure that the exponent is odd. Remember, there aren't easy ways to factor things like this or like this. We have to be clever and use something like Sophie Germain if that's absolute, or find another way out of it. So it's gonna look slightly different. We're adding here, and we're gonna alternate in here. Plus, minus. And it turns out that we always end with a plus. Right, the example is, let's do x to the 5th plus y to the 5th, all right? Just the same thing that we had before. So we start by adding x to the 4th. We're gonna subtract this time. Then we're gonna add. Then we're gonna subtract. Then finally we're gonna add. So now, in addition to like sort of like the balance of powers, just like shifting the powers all the way from the x to the y, we have plus, minus, that type of business. All right, thank you for the recap. Those are some nice looking ASCII exponents, by the way. Great question. Why does it only work for odds? Because when you try and do this logic for evens, you just, actually, let's do that. X to the 2n minus y to the 2n. We want to turn this into x to the 2n plus y to the 2n. So let's try the same thing here. X to the 2n minus negative y to the 2n. Unfortunately, this negative over here kind of fizzles away. So we're just left with the same thing. By using this trick that we used here, we actually don't get anything different. And that's the main reason why it doesn't work. All right, another note, we can do clever things. All right, we can do something like x to the 6th plus y to the 6th. These are both even, but we can write them like this. And now you see that this is sum of cubes. Hopefully so. Little tricks like that are going to be what's get you the problem solved. All right, the next one I believe that we have is going to be this. All right, this one's a bit easier to handle because it's not a general thing. So how can we do this? Well, y equals x squared. That's a great idea to start. We had to basically just think about factoring this. Think of it as a polynomial. It's a great idea to always try. Unfortunately, we cannot factor this well. So we're going to have to try something a bit different. I'm seeing a lot of people mentioning difference of squares, completing the square. All right, if we were to complete the square here, we'd have to add an x squared and subtract an x squared. So we get x to the 4th plus 2x squared plus 1 minus x squared. All right, this is very similar to the Sophie Germain business that we did earlier. All right, adding the two things and subtracting the two things. Like that. Okay, hopefully you'll see how this works. Again, this is really similar to what we did with Sophie Germain. All right, and then finally, we have one more factorization. This one's really hard. I don't actually know how to derive it cleanly. I've always just memorized this. But it actually comes up in a fair amount of places. Anybody happen to know this off the top of the head? Massive kudos to you if you do. All right, not seeing a lot of chat activity. All right, a couple people know it. That's cool. But the main idea is let's see how we can derive this. All right, and there's going to be one thing that you have to memorize, and that is that this is a factor, x plus y plus z. Just fundamental symmetric thing, so hopefully that's easy. But now we have to think, what's going to go in this other factor? Can anybody, somebody, preferably somebody who doesn't know the factorization, think of what terms have to go in here? All right, for example, yeah, we have this x squared. We have this x cubed term right here. I see x squared, y squared, and z squared. Excellent. And that's because in order to get this x cubed, we could do it like x times x squared. To get this y cubed, we do it like y times y squared. Same thing for the z. But if you multiply this all out, you get terms that you don't like. You get like an xy squared term, an xz squared term. This should be a 2. Sorry if there's any confusion. And like a yx squared term, and a yz squared term, and a zx squared term, and a zy squared term. And we need to subtract these out, and we get rid of it with negative terms. And remember, with these negative terms, we're going to have to combine it with things here. So let's say we need to get rid of this xy squared that occurs from this multiplication. What is a negative factor that we could put in here? And I see xy, and yes, that's exactly what you want to do. Right? Remember, we have to subtract it because we want it to cancel out. So then y times negative xy is negative xy squared, which cancels this out. And then you'd have to go like this, and you'd have to go like this. Oops. And it turns out this works. And this is the factorization. So this is a really advanced one. It's not used often. We'll encounter a problem that does use it in a couple, so just keep it, just be aware of it. For now, let's go on to the next problem. How do you figure out that x plus y plus z is a factor? Basically, like if you want to get really rigorous, you plug in x equals negative y minus z, and you get that the whole thing is equal to 0. Otherwise, you just like memorize it. Motivating stuff that's taught to people is difficult because there were mathematicians who didn't know what it was. That's just how I remember it. Let's move on to our problem. All right, and this is a great example of like how we have to be clever about factorizing things. All right, let me type these numbers into the chat. Just think about how might we do this? And I encourage you not to try and expand these out. Should be a 471. Because no person ever wants to be spending time evaluating 343 or 471 cubed even. Because that's a lot of multiplication, which means you're going to be wasting a lot of time. All right, hopefully, okay, I'm going to switch over to the whiteboard right now. Ben was just the person who happened to be on this problem. I'm seeing ideas. I see factor. Factor, that's nice and vague, but it doesn't tell me anything. Oh, questions I forgot to answer. About the negative 3xyz for the earlier one. It happens to like magically fall out once you include everything. So what were the numbers? 215 cubed plus 343 cubed plus 471 cubed. All right, I know what I thought was like, ooh, let's subtract this, use what we already learned, and then maybe add it back in, but I wasn't really inspired by this approach. All right, but what I knew was that there definitely has to be a trick. All right, I see an idea of find the greatest common factor. That doesn't really work too well here. It turns out they're all relatively prime. Prime factorization. I see. Okay, yeah, prime factorizing all of these doesn't really help because they're all relatively prime, which means it's going to be difficult. Roots of a polynomial. This polynomial would be massive, just coefficients that you don't want to handle. Right, estimation. You don't want to estimate because I'll also make a note. Find largest prime divisor. This is our goal. And if we're finding prime divisors, we need to be exact. Go to next question, look at the answer key. Those are excellent ideas that would give you the answer, just not in the competition. There is one that I've deliberately been, one suggestion that's occurred a couple times that I've deliberately been hiding. That involves that we have to look at these numbers, think critically. Like these are big numbers. Like we have to be able to do something nice to them. All right, they probably have some like magical relation to each other. I see a couple people have it. Nice observation. And it all boils down to this. This is an arithmetic sequence. This is plus 128 right here. This is plus 128 right here. And if you're picking random numbers, you probably would not get an arithmetic sequence. And look, we have 7 cubed in the middle. This is a perfect power, and we have 2 to the 7th, like a bunch of perfect powers. So maybe this is the right idea. But it's tiring to write all of these numbers because they're long numbers. So I'm just going to replace this with x and this with y. So we have x cubed, x plus y cubed, x minus y cubed. And this is great because now that we have like this and that, I know that things are going to cancel. So let's expand, all right? Hopefully all of you see where I'm getting this. I'm going to write this one deliberately underneath, because then we can see the beautiful cancellations even better. All right, look, magic, more magic. So in all, once we collapse everything, we have 3x cubed plus 6xy squared. Well, what can we do with this? That's a lot easier to see once we got to the variables. We can factor, yes. And what are we going to factor out? I see a lot of 3's, I see a lot of x's, but most importantly, I see a lot of 3x's. All right, cool. So now we have to compute 343 squared and add 2 times 128 squared and factor that. That's massive. By the way, maybe now would be a good time to plug some stuff in. So I'm gonna, hopefully you all have the problem written down somewhere at least. All right, so 3 times 7 cubed. And also now that I have all this factor, might as well write them out. Plus, this is 2 to the 7th, so we're actually adding 2 to the 15th right here. All right, so we see that our small primes are going to be 3 and 7 because they appear right here. But now this is a massive number, and oh, it looks like we can factor it. People are telling me. I want everybody to think, how can we factor this? You only need to tell me once. All right, somebody says bash. I like what you're thinking. I see a Sophie Germain. That doesn't really work because we have odd powers here. I see sum of cubes. That's great. All right, how do we motivate the sum of cubes? Well, we notice that 6 and 15 are both composites. All right, yes, that odd power thing. So we can do it like this. And going back to an earlier comment about prime factorization, I kind of dismissed it there, but I really shouldn't have, because that's exactly what we're doing right now. Like, because using the prime factorization to get these nice exponents to factor. All right, so how does this look? Let me clean up some space. It appears I massively overestimated or underestimated the amount of time I need to spend in these problems, so we might go a bit long. Sorry if we do. So 49 plus 81. All right, remember sum of cubes, we have to alternate the signs. 49 squared minus 49 times 81 plus, oh, where did I get this 81 from? I'm sorry. Thinking a bit ahead. Plus 32. All right, and I thought of the 81 because I knew what this was going to be in advance. This sum is 81, 3 to the 4th right here. So we know that we can discard it because this is not the largest prime. But this probably is. So let's compute it. 2401 minus, this is 32 times 50 minus 32. So that's going to be 1600 minus 32. So that's 1568. I said 5, but wrote 8. And then we add 1024. All right, so can anybody who can actually add tell me what this works out to be? Okay, I'm going to trust you when you say 1857. I'm getting a lot of different answers. It should end in 7, so okay. And this looks prime, so actually, no, it doesn't. It really doesn't. We need to check if it's divisible by 3 or 7. Is it divisible by 3 or 7? Yep. Okay, this looks more prime. All right, is it divisible by 3 or is it divisible by 7? 619? No. So this should be prime. And because the problem tells us that there are only 3 primes, we know it has to be prime. So we're done. In total, I think this is like 3 to the 6 times 7 cubed times 619. So you see, just using a bit of sense and noticing that we had this arithmetic sequence converting to variables, because it allows us to see factorizing a lot easier. And it saves us the trouble of just writing out stuff over and over and over and over again. All right, I'm gonna have to go to the next problem. All right, and this next problem is gonna be fun. Because it's Putnam. For those of you who don't know, Putnam is a college competition. Fortunately, not all their problems use college level math. This is one of them, actually. So let me type in the main equation. All right, we're actually going to simplify this. Like once we have the graph, figuring out the equilateral triangle is more or less straightforward. So I'll sketch that, but this is the main equation that we're working with. All right, we're going to need to figure out what this graph looks like. All right, we do not want to use Desmos because Desmos is cheating. Okay, thank you, Brian, for that well thought out summary. Okay, so all right, now that I have that equation, let's move on to the whiteboard, see what we're dealing with. Okay, so we have to stare at this and we have to think, we got to factor it somehow, because graphing this really does not seem obvious. All right, we can't use graphing calculators. We got to use our own craniums. No calculus will be required. I mean, this is really hard to see. All right, because we have this x cubed and this y cubed. These are degree 3, meaning they have 3 variables. But this is degree 2, meaning it only has 2 variables. All right, I'm seeing a lot of sum of cubes, but it won't really mix nicely with this. I'm seeing a lot of ideas. Nobody's quite hit it on the head yet, so I'm gonna have to give it away because we're running out of time. I'm really sorry. I know you'd all love to bash your head against this problem a bit more as I did. All right, and it turns out we have to use that really hard one from the beginning. That's why it's nice to have it. And nope. Wait, what am I saying? What is the instructor talking about? Is he crazy? This one has a z, and there is no z here. All right, how can these possibly be related? Oh, I see, you all have it. All right, we put z to be equal to something like an actual number. All right, I'm seeing a lot of 1s, but that actually isn't the case, which you'd see once you wrote it out like this. And this would come naturally when you try to factor it. Not that z is equal to 1, it's z is equal to -1, yes. So now we got to factor this, right? And hopefully somebody remembers how. The way I remember it is, oh, this is the thing. So we have to add all these. So we have an x plus y minus 1. And over here we have x squared plus y squared plus 1 minus xy plus x plus y. So we have this. All right, let's say that, okay, so one or the other of these factors has to be 0. Everybody see that? So if x plus y is equal to 0, we get this graph right here. So that's one case. So we've already found an entire thing. At this, yeah, we're just trying to find the graph of this, what this looks like. All right, so now we have to set this equal to 0, and this is where like some like hard factorization stuff comes in. All right, so let's focus specifically on that right now. And it turns out that we can use a trick that I didn't really mention earlier. All right, and that trick is called completing the square. All right, how am I going to complete the square? All right, this is a conic section, but it's a special one, as you'll soon see. Well, the idea is that you can multiply everything by 2. And basically, you get x squared minus 2xy plus y squared on one side. Then you have x squared plus 2x plus 1. And then you have y squared plus 2y plus 1. You see how that's this multiplied by 2? How I split apart these? So what do I get? X minus y squared plus x minus 1 squared. Okay, so we have a bunch of square numbers that add up to 0. Oh, it should be x plus 1 squared and y plus 1 squared. Thank you for the correction. All right, what can we say about each of these squares? If you have a bunch of squares that add up to 0, they're equal, yeah. But we can say something a bit stronger. Yeah, I'm getting enough. They all have to equal 0. Because if not, that means that this is positive. No negs, as one of you guys said, and nicely put. So, what is the only solution to this equation? So, really surprisingly. If we set all these equal to 0 and we solve these equations, we get a single point. Right here. All right, and you see that's because we complete the square and it works out so nicely like this. So now the actual problem asks us to find the area of this equilateral triangle. And the way that you do that is you figure out this length and use 30, 60, 90 triangles, but that part's boring. The interesting part is what we did here. This was our main magic heroic step. Yep, we did it. So this is really extreme, but it shows you just kind of the kind of things that you can do just by noticing these nice factorizations. Yep, that was a putnam problem, and we did it. No problem. Let's go back. We're gonna get into a bit of theory. I'm gonna kind of breeze through these because these are a bit boring. These are symmetric sums. All right. And the idea with symmetric sums is that we have these symmetric terms. All right, let me get the pointer. We have x plus y plus z. We have x, y, z. Like we see each of these are symmetric. Every combination of 2 terms, every combination of 3 terms, every combination of 1 terms. And it turns out that we can write all of these in terms of SPNR. So I'm only going to do number 2 because the other ones are like sort of similar ideas. So let me write out everything on the whiteboard. And oh, whoops, I just shared the exact same screen. All right. X squared, y squared, plus y squared, z squared, plus x squared, z squared. All right, so S was equal to x plus y plus z. Hope for sum, P for product, and R for R. All right, so what does this look Sorry. Which one does this look like similar to? Thank you for the blesses. All right, we need to figure out this. So we should probably start with the term. And I want to start with r, because there's an xy here and an xy here. But it's a bit different. We have to go 1 power up. So we're going to have to square this. So r squared is equal to, oh, look, we start with exactly what we want. But now we have all this garbage over here. So we're going to have 2 times xy squared z, multiplying these two together, plus xyz squared, multiplying these two together, plus xy squared z. Am I going too fast for anybody? Is anybody wondering how I got here? All right. Please let me know if you're struggling, because, okay. Basically, when I square a plus b plus c squared, all right, we have to like multiply every pair of these. So it turns out it's going to look like a squared plus b squared plus c squared, but the other term is going to be 2 times ab plus bc plus ac. This is what happens when you multiply it out. Please trust me on this. All right, there was an error here. That term should not have been repeated twice. This times that. So that's what I did here. I got this term from multiplying out these two, this one from multiplying out these two, this one by multiplying out these two. Okay, is there any way, okay, this is the garbage, what we want to get rid of. Is there a nice way that we can get rid of the garbage? Is there any way that we can rewrite this to make it a bit friendlier? Right, we can factor, yes, always factor. And we can factor out, we see that there's an xy and a z in all of them. And even better, this stuff can be broken down into our fundamental units. Hopefully you see what we did. We started with like a base. All right, what we wanted to start with. And we just squared it to match it. And then we saw that we had extra terms. So we had to subtract those out in a certain way. And maybe you will have more steps, but in general, this process will be the same for each of them. All right, just like starting with something, adding it out. Like if by chance subtracting out the garbage introduces more garbage, you might have to add some more stuff back in. Hard to tell between the 2's and the z's. This is fair. I will do my best to fix that. Hopefully that's better. All right, nice. So those are like just like symmetric sums, and we're gonna see really quickly a problem where we can apply that. Sort of similar ideas. All right, this might be a bit of a stretch, but I happen to like this one. So let's actually experiment with using the whiteboard on here. All right, so oops. Okay, no, this doesn't work. Purple Comet is a math competition. All right, I'll rewrite the question once I switch over. All right, so hopefully you guys have enough time to see it. Okay, so we're given m squared minus n equals 32 and 5th root of m plus root n plus 5th root of m minus root n. Yep, we have, oh, it's a roots of this polynomial. To the 5th minus 10x to the 4th, 10x cubed. This is a root. Oh shoot, am I sharing my background? Huh. Oops. Okay, hopefully that should be fixed. Okay. So we're gonna need to figure out how to manipulate this. All right, so one trick that we can do, we have this m squared minus n condition. Can anybody see how it like might relate to what we have here? Okay, so let's just go on with it. Okay, so a common trick is to let this one be equal to A and this one to be equal to B. All right, think of these as two things. And now notice we have all of these, which means we're having a lot of symmetric sums. All right, so symmetric sums means that we need A plus B, which is what the answer, and we need AB. Can anybody tell me what AB is equal to? You see that when we multiply these, we have to multiply the insides. So we multiply these two, but this is a difference of squares. So when we multiply A and B, we get the fifth root of m squared minus n. That's the fifth root of 32. So that's 2. Nice. Okay, so let's think. How are we going to write? Let's rewrite this in terms of A and B. Because we need to figure out what m and n is. Yeah, that's the end goal. So what do? We just substitute it in. Okay, my 2 looks like a z. Just know that it's not a z because I won't be using z anywhere here. All right, a plus b to the 5th. All right, this is the binomial theorem, just expansion using FOIL. A to the 5th. 1, 5, 10, 10, 5, 1 are the coefficients. And we know that because of Pascal's triangle. It's going to be a bit cramped. But you see how I'm just passing over. Oops, what am I doing? Passing over the exponents. All right, 0, 5, 0, 4, 1, 3, 2, 2, 3. So I have this. And let's try and make it look symmetric. All right, we have a plus b is equal to this. All right, so let's try and group and maybe apply what we have. So let's group the a to the 5th and the b to the 5th. There's not going to be a lot that we can do with it right now, so let's just leave it aside. But you see? So next we're going to group the 5 a to the 4th b and the 5 a b to the 4th. Again, symmetry is nice. So we have 5ab times a cubed plus b cubed. All right, but what did we say AB was? We said it was 2. Look at the top left. So this is actually a 10. And now we have, this is going to work out to be 40 in the middle because we have a b squared, a squared, we have 10 a squared, b squared. So we multiply by 2 squared. Nice. So that's the first term. Now we need to subtract 10x cubed, which is 10 times a plus b cubed. So we had to subtract 10a cubed. Oops. Minus 30, because 3 times 10, a squared b, minus 30 ab squared, minus 10 b cubed. So let's group like we did before. Minus, and then when we factor out AB, this becomes 60. Oh, look. You see this? You see this? You see what happens here? Isn't it just so nice when things cancel? And you can just scratch them out as if they're not even there. All right, and we also see like minus 60 times a plus b plus 40 times a plus b. All right, that's going to sort of cancel. But look, we have to add 20x. So there's actually also going to be a plus 20 times a plus b. Oh, no. Can everybody see? Okay. Minus 40. So we see plus 40, minus 60, plus 20, 0. So we're just canceling all over the place. And this is a minus 40. So after all that, what we're left with is a to the 5th plus b to the 5th minus 40 is equal to 0. A to the 5th plus b to the 5th is equal to 40. So after all this work, just because we've written everything symmetrically, we arrive at this equation. So based off this, I want you to tell me the value of m. See if anybody sees what I'm getting at. Tell me what m is. I want to know what m is. Getting a lot of 20s. Yes, that's exactly what it is. Because you see, when we raise this to the 5th power and we raise that to the 5th power, this is going back to the original definitions of a and b, and we add them, we get 2m is equal to 40, m is equal to 20. Okay, what is n equal to? And let me know, how are you getting this number? Right, and I see a lot of people are going back to this equation. That's exactly what we do. We plug in n, m there, and we get that this is equal to n. And just like that, we're more or less done. I think the problem asks us for m plus n, which is like 388, but the answer format doesn't matter. We figured out everything about the question. So this is why like looking at the symmetric sums are really important. And we noticed that group powers, this can actually be sort of rigorized in the section that we're gonna just go over. I have an entire section that's I haven't even gone to because I did not expect I would be explaining for this long. So that's on me for just taking a long time to explain things. If you guys can go, it's fine. It's not too important and it will all be in the handouts. If you have any, if you want to ask me more questions about it, just message me in Discord. All right, so let's go back to here, and we're just going to go touch upon these a bit quickly. These are called Newton sums. Basically, this is a way, class is not over. There is a lot of stuff that I need to cover. I'm just going to go through it really quickly. So stay if you need to, go if you need to, stay if you want to, go if you need to. It's anything. Just, but the idea is that basically a lot of the most important symmetric sum, the one that we care about mostly, is going to be r1 to the k plus just the sum of the kth powers. And it turns out that this is just about as long. This is a set of formulas that allows you to get these really efficiently. Right? I have personally never used these. I've only ever seen a use for them once on like an AMC that was last year. So I doubt they'll be using that again anytime soon. What I'd rather use is just the methods that we do here. All right, just deriving things just from the bottom up, canceling, subtracting, and adding back as necessary. Hopefully class will only be about like 10 to 15 minutes longer. I'll try and go a bit fast. So please take advantage of the video if you are confused. All right, if you really want, there's the application problem for this is in the back. So let's go on to, okay, the final thing I'm talking about. It's sort of a meme in the Olympiad math community, and this is called the functional equation, or the FE. All right, basically it looks like you're given a polynomial, or you're given a function f of x that satisfies these properties. Determine all the possible values of f. And so instead of solving for a single variable, you're solving for an entire function now. All right, and we're just going to restrict ourselves to polynomials because these come up, and just let's just think, what are we going to do with these polynomials? Like, what are we going to do? All right, and it turns out that basically every single functional equation like this that you will ever encounter satisfies the following prime directive. When in doubt, always plug in. Or just plug in every possible value you can imagine. Plug in x is equal to y, plug in x is equal to negative y. You'll see what I mean later. Plug in 0, plug in 1. But always just be plugging in because that gives you equations to work with. And that's better than just like staring at the problem, trying to use the method of divine inspiration to find these solutions or something. Because if you're using that, how are we going to prove it? Let's see an example of what we're talking about. Just a simple one. All right, and let's just think how we're going to solve this. All right, and a great thing with polynomials is that both the left side and the right side have to look exactly the same, because they take on the same values infinitely many times. So in this case, what we're going to be able to do is we're just going to be able to plug in stuff. All right, plug in the definition of a polynomial. This is the equation. All right, and this is what polynomials look like. Like that. So when we plug this in, we get on the left-hand side whoops. And all the way to, all right, this is going to be using acute bit of logic. And on the right-hand side, we have a0 plus a1 x plus, and then we're also going to be adding for the y. Right, I see that the top is distributive property. This is not necessarily true. Not all functions follow distributive property like this. Because we see that not every polynomial is actually going to work. Let's think. Is x plus y squared equal to x squared plus y squared? Yes or no on this? I am getting way too many yeses than I am comfortable. X squared plus y squared. I'm getting way too many yeses than I'm comfortable with. These are not the same. What if you plug in 1 and 1? You get that 4 is equal to 2, and then the universe explodes. Don't make 4 is equal to 2. Right? Polynomials look the same if they look the same on both sides. So we say that p of x equals x squared. It's not a solution. And I'm running out of space inside. Okay, anybody have any guesses for solutions? Because that's also how it starts. We have to guess solutions. Right, some people have it. I see 0. P of x equals 0. That's a wonderful solution. Yes, 0 is equal to 0 plus 0. And that is correct. And all is right with the universe. All right, and I see another. P of x is a linear function. That. So we have cx is cx plus y. And it turns out that in this case, we can make the distributive property behave nicely because we're assuming the function. So we think that these are the solutions. Can anybody think of any different solutions? And the answer will be no, because there are no others. And this is why. Sorry, I have to go fast because people are leaving as I speak. All right, and the reason is because anytime we have any higher powers, that means these x's and y's are going to begin to mix. And they mix on this side because we're expanding this and we have binomial theorem stuff. But they don't mix on this side because there's this big wall dividing them, this plus sign right here. And we can't have things mixing on this side, but not mixing on the other side. That is logic that you can actually use. So we have to draw the line right here. So we know that all these terms are just going to not exist. But when we set this equal, we also see that A0 has to be 0 because we have the equation A0 is equal to 2A0. All right, please do not spam my chat. I cannot, that makes it harder to see like actual questions. So that's how we arrive here. All right, this next one will be a more concrete example. All right, and it uses the other properties that polynomials have. Polynomials generally have two forms. That should be the moral of the story. That is, they have their coefficient form and they have their root form. This is a great exercise in root forms. And it's also a great exercise in what should we plug in? So I'm going to go ahead and write the equation. We'll get started. We cannot divide by x plus 1 because this is not really a factor. Okay, so let me ask this to everybody. I said the prime directive was to plug in stuff. What should we plug into here? I see a lot of zeros. That's a great instinct. I see some negative ones and I see some tens. All right, so let's try both of them. Let's plug in -1. We get this side is 0. That's a good instinct. Then we get that p of 0 is equal to 0. We plug in 10. We get this side is 0. And p of 10 is equal to 0. Nice. Right. Okay, we're just, the question is, we're just solving this. We're solving for p of x. And remember, p of x is a polynomial, which means that we can't do like, yeah, so we see that we have factors. We actually have two factors as a result of this. All right, x is a factor. And x minus 10 is a factor. Okay, so now that we have this in mind, I know that p of 0 is equal to 0. We can use a similar trick to plug it into here. And we get p of 1 is equal to 0. Somebody's asking me to try p of x is equal to x plus 1. Like, just stop here. Well, remember, we also have that x is a factor. So, and I actually don't know that -1 is a factor. So, all right, so now that we have this information, if we plug in 1, we plug in 1, we get p of 2 is equal to 0 now. All right, you see, because this side becomes 0 and this becomes, and you get the picture. All right, we're going to keep on continuing. If we plug in 9, if we plug in 8, we get p of 9 is 0. If we plug in 9, we get p of 10 is 0. But we already knew that. And if we plug in 10, we get 0 is equal to 0. So we're stuck here. So we know that p of x has all these factors. And that means that it looks like x times x minus 1 all the way up to x minus 10. But we also don't know whether there's like another polynomial, q of x. So, all right, I see plug it in. That's an excellent idea. So let's plug it into here. So we get on the right side, x plus 1 times x times all the way to x minus 10 times q of x is equal to, all right, and on the right side, it turns out we get the exact same thing, except this time, we get q of x plus 1. So we can cancel out all this. And now we have this equation up here. All right, and how are we going to solve this? All right, can we like say anything about q? Just from this. It turns out that we can say that this is a constant. Not just 0, but any constant at all. Q of x could be equal to 5 or something. I don't know. Q of x could be equal to like pi to the eth power. All right, and why is this true? And the reason is just like something about the graphs of polynomials. All right, if this is true, that means that like we have a situation like this, where all these values are supposed to be equal. These are all q of x. Yeah, it could be equal to e to the I pi, q of x. All right, and this means that the polynomial is always going to be like, just like sitting around here. And if that's the case, then like it can't have any higher terms. It can't have an x term. It can't have an x squared term. Because x squared, x cubed terms, they like to get bigger. And this doesn't ever get bigger. So we see this equation and we think, what do we know about polynomials? We know that they get bigger unless they're constants. So that's why we know that q of x is equal to a constant. And this means that we're done, actually. We know that p of x is equal to some constant times x minus 1, all the way down to x minus 10. Perfect. So everybody see what we did. We just plugged in stuff, found information about the roots of the polynomial. Once we like found all the information we could, we made a guess, and it ended up being right. All right, there are some practice problems in there. It would actually be really cool if people would like talk about them in the Discord. Get some actual like math discussion going in there. All right. And that is all I have for today. I know I went really over. Very sorry about that. All right, hopefully all of you found something interesting for today. All right, please send me any questions that you have. If you have them, talk about them in the intermediate Discord, in the intermediate channel of the Discord. All right, I would love to see like math discussion. All right, you can find me. I am part of the staff in the Math Divulge Discord. I'm usually always on, so I am perfectly able to answer any math-related questions that I am able to solve, of course. So let me stop the recording.